Hey, what's up guys? In this video we're going to do some introductory examples of how to solve systems of quadratic equations. Alright, here it is. What's up guys? So solving systems of quadratics works very similarly to solving systems of linear equations, which you're probably very comfortable with at this point. But before we get into the example, I want to sort of make something clear here that, remember, quadratics visually are represented by parabolas. So if we're talking about a system of two parabolas, well then there's a few situations that we could have. Either those parabolas intersect at two different points, in which case we would have two solutions to the system. The parabolas could intersect at one point, in which case there would be one solution to the system, or they could not intersect at all, so we'd have no solutions, or they could be the exact same parabola. So if we have two equations that look different but turn out to be the same, then we know it's the same parabola, and so there would be infinitely many solutions to the system. So in this video we're just going to stick with, we're going to start with examples where there's two solutions in the system, so there's going to be two intersection points. Alright, so the methods turn out to be the same. We could use substitution or elimination, just like as if these were linear equations. So I'll do substitution just because we're set up very nicely for substitution. Since y equals this expression and y also equals this expression, then I can just substitute this expression here in for y. All right, I can just set these two expressions equal to each other. So this is substitution. When y is by itself in both equations, I can just set these expressions equal to each other. All right, and now we're just going to solve this equation like we would a normal quadratic equation. So I'm going to get this into standard form by getting all of these terms over to this side so that one side equals 0. Actually, just to keep my leading coefficient positive, I'll get all of these over to this side. So I'm going to add 2x squared to both sides. I'm going to subtract 9x from both sides. And then I'm going to add 7 to both sides. Okay, and the reason I'm doing that is because I'm trying to get this in standard form, or one side equals 0. So I want to cancel all of these out. So what I'm left with is x squared plus 2x squared, which is going to be a 3x squared. And then we have a negative 6x minus a 9x, so that's going to be minus 15x. And then positive 5 plus 7 is positive 12. And again, this is going to equal 0 because all of these terms are going to cancel. All right. And now there's a few methods to solve quadratics, right? There's quadratic formula, there's factoring by grouping, or you could factor out a GCF, but in this case there is no, there is a GCF in this case, which is 3. So I'm just going to divide both sides by 3 here, since 3 goes into all these terms. So I'll divide both sides by 3. Alright, so we have x squared minus 5x plus 4 equals 0, because 0 divided by 3 is 0. And now I can simply factor this trinomial here. Alright. So this factors into the quantity x minus 4 times the quantity x minus 1. Alright, and now I can solve this equation, and we see, using the zero product property, that x is going to equal positive 4, or x could equal positive 1. So this is where the two solutions is going to come into play here. Alright, but remember, solutions are ordered pairs, right? It's where on the graph the parabolas intersect. So just having an x-coordinate is not good enough to tell me where the parabolas intersect. I also need their corresponding y coordinates. So what I'm going to do is I'm going to take positive 4 and substitute it into either one of these equations. I'll pick the top ones because it looks a little bit easier. So I'm going to do 4 squared, right, x squared, so 4 squared minus 6 times x, that's going to be minus 6 times 4, plus 5. All right, and then we're just going to simplify this down. So we got 16 minus 24 plus 5. All right, and so this is going to equal negative 3. All right, so my first solution is going to be 4 comma negative 3. That's the one ordered pair where these parabolas intersect. And now I'm going to repeat the process, but for this x-coordinate. So I'm going to take this x-coordinate and substitute it into the same equation. All right, and so we have 1 minus 6, which is negative 5, and then plus 5, which is 0. And so the second solution is going to be 1 comma 0. Okay. We'll do one more. So here we have, again, 2 quadratic equations. We have 2 parabolas. And in order to set myself up for the substitution method, I could, since y is already isolated here, I could just take this expression and then substitute it down in here for y. But if you prefer to get y by itself in this equation, then we can go ahead and do that as well. But I'm just going to go ahead and substitute. So I'm going to recopy this bottom equation here, except instead of y, I'm going to write negative 4x squared plus 4. So I have my negative 2x squared minus 3x. Now instead of plus y, I'm going to add this expression. I'm going to put this expression in parentheses for now. Okay. And now I'm going to really quickly clean this up a little bit so I can get rid of these parentheses. So I have negative 2x squared minus 3x, and plus a negative is just going to be minus 4x squared, and then plus a positive is going to be plus 4 equals 4. All right, and now just like my last example, I'm going to get this into standard form. So I want everything on the one side. So I'm going to subtract 4 from both sides, so I can get this to equal 0. And that is also going to be 0. Okay. And now I'm going to, I could simplify some more here. So I have a negative 2x squared minus 4x squared. So that's going to be a minus 6x squared minus 3x equals 0. All right. And now what I can do is I can factor out a greatest common factor here. So the greatest common factor of negative 6x squared and negative 3x would be negative 3x. So I'm going to factor out my negative 3x. And then negative 3x times what would give me negative 6x squared? Well, that would be 2x. And negative 3x times what would give me negative 3x? And that's just going to be a positive 1. Okay. And now, again, I can use my zero product property here. So in order to make this expression 0, x could just be 0, right? Because if this was 0, then -3 times 0 is 0, and 0 times anything is going to equal 0. But this here could also equal 0. All right, if this factor 2x plus 1 equaled 0, then the whole thing would equal 0. So if I had 2x plus 1 equaling 0, and I solved that for x, I would see that x could also equal -1/2. All right, so again, we have two x coordinates here, and we need to see what their corresponding y coordinates are. So I'll take x equals 0, and I'll substitute it up into this top equation. Looks much simpler than this one. So I have y equals -4 times 0 squared plus 4. Okay, again, I took this 0, and I substituted it for x. And then after simplifying, this is just going to equal +4. And so my first solution is going to be 0, comma, +4. And then I'll do the same thing with -1/2 here. So I'll substitute -1/2 into this top equation. So we have y equals -4 times -1/2 squared plus 4. All right, and we'll simplify this down. -1/2 squared means -1/2 times itself, which is going to be a +1/4. And -4 times a +1/4 is going to be a -1. And -1 plus 4 is +3. And so my second solution is going to be -1/2, comma 3. And these would be the two intersection points of these two parabolas. All right, so in the next video, we'll do some different cases where maybe we end up with one solution or no solutions or infinitely many solutions. All right, and with that said, it's been demonstrated.